Okay, so we're all good. So today's lecture, which I think will actually be the last lecture for the course, we'll see how we go. But I think even if I go a little bit over time today, I think this should basically finish up a nice section of Fell bundles. So rather than trying to start some kind of new topic for for next week, I think it's probably best to just make this the very last lecture. So today I wanted to talk to you about sections of Fell bundles. So just to recap, remember last week we were talking a lot about Fell bundles, right? Fell bundles over a tile group weights. So these are, in particular, Banach bundles. So bundles of Banach spaces. So you have some continuous open map row from B onto G. B is the total space, G is the base groupoid. Such that moreover, so each of the fibers is a Banach space, definitely. That's part of being a Banach bundle. But moreover, the total space B and the base space G have some compatible product structure. So specifically, B is what's known as a topological star semigroupoid. So it has a partially defined product, it's a semigroupoid, it has an evolution star, and all the operations, right? The star, the product, these are in particular continuous. Okay, and G is an tile groupoid, and we've certainly talked a lot about them up until now. Okay, what we also need is for rho to basically preserve the product, and not exactly, or not just preserve the product, but really be what's known as a star iso cofibration. So essentially that means the product in B is defined precisely when you map it to G, and the product there is also defined. Okay, and the product also has to be compatible with the additive structure. It has to be bilinear, right? And we want these sort of standard norm properties as well. So we want the norm to be submultiplicative, as long as the product is, of course, defined. Right? And we want it to satisfy the C star condition, essentially. I guess it's not exactly the C star condition because we're not dealing with C star algebras, we're dealing with these bundles, but it's essentially the same thing, right? The norm of B star B has to be the norm of B squared. And moreover, these unit fibers do indeed form C star algebras. And we want B star B to always be a positive element within that corresponding unit fiber, right? The other fibers maybe not, they do not form C star algebras in general because there's no product within the fiber. This only occurs at the unit fibers, right? But in those cases, they will be C star algebras and everything will behave nicely. So our primary interest in Fell bundles is that they allow us to define sections, and we're going to try and use these sections to define C star algebras, right? Okay, so remember, a section is officially at least just some right inverse to the bundle map rho, right? More intuitively, what a section really does is it just picks out an element from every single fiber, right? And I think we did briefly get to talking about convolution. So if we have two sections, then we want to define their convolution in the usual way, like so, right? So because FH is defined, the product of AF and BH is defined, and sometimes, not always, we will then be able to define the sum, like so. So more precisely, when we say that AB is defined, the convolution is defined, what we really mean is that for every point in the base groupoid, this sum here makes sense, that the finite partial sums here do actually converge, right? They converge in the norm topology within the fiber, which is also, as we showed, exactly the same as the topology, the subspace topology of B, right? This was one of the elementary facts about Banach bundles. So to say that AB is defined means that all of these partial sums at every single G do indeed converge. And so we can indeed, get a well-defined new section, AB, like so. For example, if at least one of those two sections there is finitely supported, then indeed AB is defined. Because if one of them is finitely supported, well, then these sums will always be finite. There will always only be finitely many non-zero terms. And so then certainly the sums converge and you can define the convolution. We also showed, I think just towards the end, a certain restricted form at least of associativity for sections. So if the convolution of A and B is defined in this sense I just mentioned, and we have some extra finitely supported section, then you can indeed show that it doesn't matter which way we take the product, right? And that indeed both of those are actually defined. And likewise, you could do it sort of the other way around. You could say that, well, if BC is defined and A is finally supported, then again, both of these are defined and equal. So that's the recap. Okay, what are we going to do next? Well, there was one more thing I wanted to recap. I think the final thing we proved last lecture was that this kind of Cauchy-Schwarz inequality. I mean, the original Cauchy-Schwarz you're used to is probably for Hilbert spaces, but we then used that and built it up to Hilbert modules, which is another sort of standard result. And then we went even further and showed that this gives us a kind of Cauchy-Schwarz inequality for sections of Fell bundles or convolution of sections of Fell bundles. So more precisely, it says this. It says the positive operator the positive element, I should say, you get by taking convolution of A and B at some element G and looking at that star times ABG, then this is below in the usual operator theoretic sense. So within the fiber BSG, which is a C-star algebra. So in the usual ordering on positive or self-adjoint elements, this element here is below this element over here. So here we have a norm of AB at G, and we have the norm of AA star, but this time at a unit, namely the range of G. And likewise, we're looking at B star B, again, at a unit, namely the source of G. Okay, and actually that in itself is probably not what we really need. What we really need is a slightly simpler inequality we get by just taking the norm. So remember, with positive elements, if you have some positive element below another positive element, then indeed the norm of that positive element is again going to be below the norm of the larger guy. Right? So if we take norms here and apply that, we see that we have two, A, B, G normed squared on the left, right? And then likewise, this B star B becomes normed, right? But then we can divide through just by one of the norm ABGs and then end up with this nice, more simpler inequality here. So this is kind of the Cauchy-Schwarz thing we will need to get started today. And we'll use this to examine, well, in the end, various different kinds of norms on the section. And there'll be several. There'll be three essentially important norms on the sections that we will need to get us our C-star algebra in the end. I mean, the whole goal really is to define the reduced C-star algebra, right? But to do this in one for Fell bundles. Before we only did it for groupoids and for complex valued functions on those groupoids. Here we want to do it for sections of the Fell bundles. And we also want to do it in a slightly better way than before, because if you remember before, to define the reduced C-star algebra, we first looked at compactly supported sections. Then we looked at this reduced norm from the regular representation and then took the completion. And the downside is that these elements in the completion now, they're no longer seen as continuous functions anymore. We want to do things in a better way so that even in the completion, if you like, our elements will still be actual concrete sections. Right? However, this will take some work. So speaking of norms, first recall the infinity norm or the uniform norm is defined just by taking the supremum of the norms of all the individual elements in each fiber coming from the section A. Right? So this you can define in any Banach bundle, right? As we did. So that's the first thing to know. And before we get to the next norm, I just want to introduce some notation. So let's say we have some section A here, and we have two subsets, F and G. Often F will be finite, but it doesn't have to be at this point. So what we often want to do is kind of restrict A to F, but it won't exactly be a restriction. We still want our new AF to actually be defined outside F. We just want to set it to 0. So it's kind of a restriction, but in a way that still gives you a total section, if you like, of the bundle. So we just say AF of G is AG as long as G is within F, but outside of F, we just set it to 0 within that fiber. So this will be important. And recall another little notational convention, which I think I introduced last time, and that is that if F is written like this as sort of a subset, but without the line, right? So if F is sort of a strict subset of G, what this really means is that F is a finite subset of G. Right? We'll be very interested in the finite subsets. So that's the infinity norm. What do we do next? Next, we want to define a so-called two norm. To define this, first note that if we have, let's say, two finite subsets, E and F, right, where E is contained within F, and if we have some element of the unit space, then if we look at the value of A star A restricted to E at that unit X, then we get this sum, right? And the sum is well defined because E is finite. So there's only going to be finitely many things in this sum here. And you'll notice that, well, each of these is going to be a positive element of the unit fiber, of the fiber at X, right? So you're taking a sum of positive elements. So if E is contained in F, then this sum here will contain more positive elements. And so therefore, the sum over this thing here has to be below the sum here within the fiber. Again, the usual ordering in a C-star algebra at that fiber. Okay, so as these finite subsets increase, you get this sort of increasing sequence of finite sums. Right? There's no guarantee that those sums will converge to anything at this point. However, we do know that the elements will increase, and therefore the norms will also increase, right? As I mentioned before, if two positive elements, one is below the other, then the same applies to the norms. So this is how we define the two norms. So we define the two norm to be basically the supremum of all these individual norms where you restrict to some finite subset. I mean, it looks like, I guess I'm restricting here just to a finite subset of A, but really you're also restricting to the sort of corresponding finite subset of A star as well. So you're taking the supremum over the norms for all finite subsets, and also you're taking the supremum over all units in G. Or put another way, if you like, you can rephrase this in terms of the infinity norm, right? So you can say what you're really doing is you're looking at A star AF, some finite F, and you're restricting that to the unit space, and then looking at the infinity norm. Right? That's another way of looking at it. And because these things increase, this is actually exactly the same as the two norm, but of A restricted to F now. So this applies in general, right? This is the two norm of a general element. Again, it's maybe not a norm in the strictest sense because sometimes these supremums can be infinite, right? Sometimes these norms can just blow up to infinity, right? But that's fine for the moment, right? We're just keep in mind that the value here for an arbitrary section could be infinite. So first thing we want to do is show a nice little inequality, which might remind you of the Cauchy-Schwarz inequality, and that is that if you have two sections and you already know that the product of A star and B is defined, it's convolution product, then it follows, in fact, that the infinity norm of the product, the convolution product, is below the product of the two norms of the corresponding elements. Right? So the norms here on the right are different, right? There's the two norms here, infinity norm here. So it looks like maybe the Cauchy-Schwarz inequality, and that's no kind of coincidence because indeed we will use this Cauchy-Schwarz inequality we just mentioned to prove this. So to prove this inequality, we have to look at all those products of the form A star B F. So we're restricting B here to F for some finite subset, right? I mean, yeah, we're looking at the infinity norm, but yeah, at the moment it surprises us to look at these Fs, right? Okay, so we're looking at this is a particular value of G. Okay, so it's really, as I mentioned, you're restricting B to F, but then because you're restricting B to F and because of the way you've defined convolution, this means you could also restrict A to FG inverse without affecting the convolution product. So this is defined, and then our previous sort of version of Cauchy-Schwarz for Fell bundles tells us the norm of this has to be below the norm of this guy over here. But this, you'll see, has to be below the two norm as we've just defined it up here. Right? So this is below the two norm of A, yeah, and this is below the two norm of B. Excuse me, at the two units, the range of G and the source of G. Right? Yeah, but as you're taking supremums over all units and all finite subsets, we know that this has to be below the two norm of A times the two norm of B. Okay, so that shows that, therefore, I mean, we know that at each individual G, right, we're saying A star B is defined, which means by definition that A star B at G has to be the limit of these A star B Fs, right? It's the limit of all the finite partial sums, which is exactly what you get when you multiply A star by B restricted to F, some finite F. Okay, so if this is true for all F, well, that means the norm of A star B at G, which is equal to the limit of this, has to be below, the norm of 2 norm of A times the 2 norm of B. And as this is true for all G, right, then that indeed means that the infinity norm of A star B has to be below exactly the same quantity. So that's our first little norm inequality. We will meet several more in the next hour or so. Okay, and one thing I just want to point out is that, again, to do with this infinite business, right? So this inequality is meant to hold even when some of the terms are infinite, right? I mean, if say the 2 norm of A is infinite and the B norm of the 2 norm of B is finite but not 0, or even infinite as well, then you know the product of something infinite and something else apart from 0 should definitely be infinite, right? So the equality in that case would be kind of trivial, right? If you have an infinity on the right. Like the only real non-trivial situation that you kind of have to carefully think about a little bit is when one of these two has an infinite 2 norm and the other has a 0 2 norm. Then you have the question of how should you really interpret 0 times infinity, right? You could interpret it as anything between 0 and infinity, but the sort of strongest statement you get would be when you interpret this as being 0. And even in this strongest form, the inequality still holds, right? And the argument is pretty simple, and that is that if you'll notice that if the 2 norm of any element is 0, well, then that's actually saying that everything has to be 0, right? All the values at every single element of your groupoid, if you apply A, you should always get 0 within that fiber. So that's fairly easy to verify. I mean, once you're taking sums, remember you're taking sums over essentially all elements in the groupoid. So the only way you could end up with a 2 norm 0 is if A was already 0. And if A is already 0, well, then A star is 0, and so A star B is also going to be 0, right? So therefore, the infinity norm of that is again going to be 0. Another thing to note is that this kind of tells us something about the original definition of the 2 norm. So we could, in this inequality up here, we could actually take B to be A, or even A restricted to some finite subset F. So in that case, this inequality is really telling you that, well, you just plug it in, right? So the infinity norm of A star AF is below these two guys. But then remember, the 2 norm of AF increases as F gets larger. So, and in particular, the 2 norm of A is the supremum of all those guys. So really, this is below the 2 norm times the 2 norm of A itself. So this is just that squared. And by definition, this is the supremum of all these infinity norms, right? Of A star AF restricted to G0. But of course, you could then say, well, let's throw away the G0. I could look at the infinity norm of the original expression A star AF. And the only thing that could possibly happen is that I get something larger, right? Okay, but now you look at this whole inequality. I've said at some particular F, norm of A star AF, the infinity norm, is below the supremum of all these guys, and I have these things in the middle. So if I take the supremum over here, then all these inequalities here must sort of collapse to actual equality. Okay, and in particular, what this tells you is that I could have taken the supremum here, right, over just the infinity norm of A star AF already. That this has to actually be equal to the same quantity where I restrict to the unit space. Okay, so originally, at first you might think this is likely to produce something larger, like a larger kind of norm. But what we've shown is that actually no, that you could delete the G0 and still this is a perfectly good expression for the 2 norm. So that will just be sort of convenient sometimes to remove a few little brackets and restrictions. Okay. What about, well, yeah, subadditivity. So I've been talking about the 2 norm as if it's a norm, but I haven't really shown you that it's a norm. I mean, we know it's it's fairly immediate that it's well, homogeneous, like that if you multiply by a scalar, then you can take the scalar outside, at least once you add the modulus function there. But it's not immediately clear, at least, that this 2 norm is actually subadditive, one of the key properties, right? But we can, thanks to this new equality we've just proved, we can indeed show this. So what happens if you take a sum of 2 sections, right? With, well, with I guess it doesn't even have to have finite 2 norm, just with any 2 arbitrary sections. Look at their sum. Restrict to some finite subset and look at the corresponding 2 norm. So you do a bit of calculations, say, well, 2 norm is of this thing, at least the finite case is just really taken by looking at the infinity norm of this star, this, then expand out, right? And they use the subadditivity of the infinity norm. So that's fairly clear, right? We know the norms in every fiber individually, they're definitely subadditive. Okay, so I can certainly do this. And then note that, well, what is this really? This is really the 2 norm of AF. This thing here is just following from the inequality we just proved in a very special case, and likewise for these guys. And in the end, you realize, okay, well, this is really just the square of the 2 norm of AF and the 2 norm of BF. And then you just take suprema, right? Taking suprema gives you the 2 norm of A plus B on the left, whereas over here, this will give you the 2 norm of A plus the 2 norm of B. So it really is subadditive, and hence it is really a norm. I mean, I guess subadditivity tells you it's a semi-norm, but as we already mentioned, if the 2 norm of some section is 0, then A has to be 0. So that tells you it's not just a semi-norm, it's really a norm. So that's reassuring. My terminology is not stupid. Okay, so next we want to define another norm, which will really be the key norm we need to define a C-star algebra. But the way to define it is to use this 2 norm we've just defined. So first, again, maybe to make life simpler, let's introduce some notation. So let's write f of rho to mean all of the finitely supported sections of rho. And to define the B norm, you look at A as if it operates basically on these finitely supported sections. So we know that if f is finitely supported, then AF is indeed defined, right? And so we can indeed look at the corresponding element, AF, look at its 2 norm, and then divide by the 2 norm of F, as long as F is not 0, right? So I guess I should have really put \0 there. Or if you like, you can interpret 0 over 0 as just 0. But, okay, so this is the standard way to define an operator norm. When you have some operator on some norm space, this is generally known as the operator norm, right? So that's all this is. Okay. First thing we want to do is show that these norms are related in the following way. So we want to show the infinity norm of any section is always below the 2 norm, which itself is always below the star of the B norm. We will soon see that, in fact, the star here is unnecessary, but for the moment, we're going to keep this star here. So how do we show that? Okay, we want to show the infinity norm is below the 2 norm. So let's look at the value, or let's look at the actual norm of A at some fixed G. Well, thanks to this C-star condition on the fibers, right? This is one of the defining properties of Fell bundle. We know this is equal to the norm of this guy here. But put another way, this is just the 2 norm of A restricted to some single element of my groupoid, some single G. And we know that these 2 norms are, increasing with respect to increasing restrictions, right? So this is in particular below the 2 norm of A, like this, or if you like, A, I guess, is defined as the supremum of the finitely supported guys. In particular, it has to be above this singleton supported restriction AG. So that essentially gives you one direction, right? Because this was true for arbitrary G. So therefore, the infinity norm of A has to be below the 2 norm of A, right? Okay, and that's okay. So that's what I'm saying here. So yeah, there's A star A, square to A. Hang on. Yeah, I think I'm. Maybe. Yeah. Yeah, I think I think there's some calculations here, or maybe I've skipped ahead a little bit, right? But yeah, no, I think I worked it out, right? So this is proving the first one, but then I want to move on to the second inequality, right? So this is already done, basically. Okay, so how do I prove the second one? Well, again, here we took some arbitrary g. Here we're going to take some arbitrary finite subset, right? And look at the infinity norm of a star a f. Okay, well that's as we just showed, the infinity norm is below the 2 norm for anything here. In particular, it's true for products of this form, right? So I'm just applying this, but now replacing a with a star a f. Right? Okay, so this is definitely true. This is what we've just proved. But at the same time, the definition of the B norm tells us that the 2 norm of this has to be below the B norm of a star, viewing this as a kind of operator, times the 2 norm of a restricted to f. Right? But again, the 2 norm of a restricted to f is definitely below the 2 norm of a itself. Okay, so in the end, you look at this and you say, well, okay, if I take the supremum over all these f's, this is exactly the norm of a2 squared. So if the norm of a2 squared is below norm of a star b, a2, well then dividing by a2 gives me exactly what I want. The 2 norm of a is below the b norm of a star. Okay, so that's hopefully clear. So that's our first little inequality relating these 3 norms. But the b norm also has some other forms that will often be useful, some kind of bivariant forms, maybe you would say. So specifically, we're claiming that the b norm could also be calculated by not taking the product just with a single f, not by operating on f by a on its own, but rather by, in a sense, using a to operate on f and at the same time on some other finitely supported element e, or e star in this case. I mean, you could put e here, I guess, but then you'd have to change the bottom to e star. The important thing is that on the left, you have some finitely supported guy, and on the bottom, you have the 2 norm of the star of that same guy. And again, we have a bit of a choice here whether or not we want to actually restrict the top part to G0. In the end, it won't actually make a difference. So to see why this is true, just to make life easier, let's denote this last expression here, where you do take the restriction to G0. Let's denote this by, again, a norm, but this time with a big B superscript, right? Just temporarily, right? Just because in the end, we want to show that it doesn't matter if we put the big B or the little b. But for the moment, let's distinguish between these 2 different norms. So take now any arbitrary finitely supported section, look at the 2 norm squares, then by definition, this is the supremum all of these infinity norms. I mean, normally you would put the finite restriction onto the right-hand side, right? But you can equally well put the finite restriction to the left-hand side. I've got gammas here. These gammas at the bottom here, these should really be G's. Sorry. Okay. So this is certainly true, but then by the definition of the big B norm, this expression over here, I know I can view this as a product of 3 things, right? AF star restricted to F. So this is again a finitely supported element, or I should say AF restricted to F star. I think that's what I really mean. Times A times F, again a finitely supported element. So in other words, we're taking AF restricted to big F as our E here in this expression. And when you do that, you see that the infinity norm there has to be below the corresponding products, right? The big B norm of A times the 2 norm of F times the 2 norm of this element on the left. And so, and again, at this point, this is when we can delete the F, right? Yeah, because we're taking the supremum over all these Fs, right? Which by definition gives us the 2 norm of A F. Right? And so that's a good start, because that shows us, once we divide by the 2 norm of AF, that in fact, you'll be left with 2 norm of AF on here, and you'll delete this guy here, and you'll be left with big B norm A and 2 norm of F. Okay. And so in particular, then divide by the 2 norm of F. This tells you that the little b norm of A is below the big B norm of A. For the other direction, I guess this is maybe even easier. So you look at this expression for some finitely supported E and F. So look at the norm of E star AF restricted to the unit space, and look at its infinity norm.
So again, this is definitely below the infinity norm of E star AF when you don't restrict. And the thing we proved before, remember that is whenever A star B is defined, that the A star B norm and infinity norm is below the 2 norm of A times the 2 norm of B. So replacing A and B here with E and AF, this is exactly what this tells you. Okay, and now at this point, we can use the definition of the little b norm to say that 2 norm of AF is below little b norm of A times the 2 norm of F. And now dividing through by these 2 norms of A and the 2 norms of F, this is exactly what tells you the big B norm of B is now below the little b norm of A. And also, it tells you something a bit stronger, and that is that if you divide by 2 norm of E and 2 norm of F, then you also end up with this expression here, which you'll notice is the middle expression in the actual statement of the lemma. Right, so in a sense, for free in this argument, not only did you show the little b norm is equal to this expression on the right, in the process you basically showed it's also equal to this expression in the middle. So these slightly different things will be useful for, well, various things, but immediately the sort of pressing issue is that this form makes it easier to show that the b norm is actually star invariant. Okay. So the first thing to note actually is that within a fiber of your bundle here, your fell bundle, the norm is also star invariant. This is essentially the same argument you would use as if you had a C star algebra, right? So what you do is you say that well, the norm of B squared is equal to the norm of B star B. This is one of the axioms of the fell bundle, that the C star condition must be satisfied. And subadditivity tells you that this is below this expression here. And then you divide by the norm of B, and so this tells you norm of B is below the norm of B star. But star is an involution, so B double star is just B. So if you replace B with B star here, well, this gives you the reverse inequality as well. So these two things actually have to be equal. So this is just for a single element in the total space of your bundle. But then it's easy to show, therefore, that well, it follows immediately, basically, that the infinity norm of the star of any section now, right, is also going to be equal to the infinity norm of the original section A. And once you've done that, we can use this new form of the B norm to show that that this is also going to be star invariant. Right? So look at the B norm of A star. Well, this is just plugging A star in this expression here, but no, there's a mistake here. So this shouldn't be a 2 at the top. This should be an infinity. That's a very important difference, right? So this should be an infinity norm here. So because it should be infinity here, that means I can take the star and I won't change the expression. The only thing I will do is change this. So it will now be F star A E. And that is exactly the little b norm of A. Okay, so yeah, sorry about that. It's a bad mistake. I'll fix that later. And it's bad because this is a very important point I wanted to make, is that the 2 norm itself is definitely not star invariant. So the easiest way to see this is to look even just at 2 by 2 matrices. So we can view this as a section of a trivial fell line bundle over a discrete groupoid with 4 elements, right? Like just pairs which correspond to the 4 different coordinates of your matrix. Right? And if you do that, then the 2 norm you can see basically of a matrix like this is really just going to be 1. It's going to be the supremum of the sort of the columns of this matrix viewed as elements of 2-dimensional Hilbert space. And so the columns here both have norm 1, right? But if you switch things around, if you look at the star or the adjoint or transpose of this matrix, then now you have 2 different columns, right? One column has norm square root of 2, the other column has norm 0. But you're taking the supremum, so in the end, the 2 norm of the whole matrix will still be root 2. So definitely norm of A and A star, the 2 norms at least, are very often not going to be the same. Right? The key difference between both the infinity norm and the B norm. So just to summarize the equalities or the inequalities we've proved so far, we've basically showed that the infinity norm is star invariant, the 2 norm is not, but this is below the 2 norm, And this itself is below the B norm of A, which is again star invariant. Next, submultiplicativity. So, okay, when AB is defined, we would hope, if this B norm really is a kind of C-star algebra norm, that we get submultiplicativity. And there is an almost obvious or naive kind of argument that would give you this, and it goes like so. You'd say, well, say AB is defined, well then certainly ABF is defined, but I know associativity holds, so I can rewrite it in this way. And then by the definition of the B norm, this should be below the B norm of A times the 2 norm of BF. And then you just apply the same to here, you sort of iterate, and then you'll get this expression here. But there's actually there's a reason why that doesn't work. I wonder if, I don't know if anyone can spot the problem here. The problem is basically that this is not justified. This inequality, not yet anyway, because while F is finitely supported, BF definitely need not be finitely supported anymore. And so we can't simply use the definition of B, which remember only applied to finitely supported guys. It was the supremum all over of A norm, 2 norm of AF over 2 norm of F, right? But only for finitely supported F. So in particular, we can't apply this to BF, right? So this is the key issue. But never fear, because this alternative characterization, together with the inequality we've already proved, this can be used instead for a more precise argument. So what we do know, however, is that if AB is defined, then certainly E star AB F is defined, as long as E and F are finitely supported. And again, by associativity, we can view this as a product of E star A and BF. Again, two perfectly well-defined sections. And then this inequality we had before tells us that this has to be below the product of the corresponding 2 norms. But remember, it's the 2 norm of the left side starred. And taking the star of E star A gives you A star E. And now we can apply the original definition of the B norm to say, okay, this is going to be below the B norm of A star, which is the same as the B norm of A. We just showed that B is star invariant, and the 2 norm of E, and the B norm of B, and the 2 norm of F, right? And then dividing through by the 2 norms of E and F, right? Then we get this expression for this alternative expression for the B norm, right? As long as we take the supremum. So taking the supremum, then this does indeed show that the B norm of a product is below the product of the B norms. Okay, so we've done enough playing with norms, but which could possibly be infinite valued, remember, for arbitrary sections. Now we're going to look at the spaces of sections we get when we restrict to sections which have finite K norm, or finite infinity norm, finite 2 norm, or finite B norm, right? And the first observation to make is that the infinity norm is, the S infinity of rho is complete, right? It's basically because each fiber is complete. So if you're looking at arbitrary sections and just taking the supremum of the norms of all the fibers, right? And that's finite. Well, in particular, if you have a sequence of such things and they are Cauchy, well, that means in each fiber they're Cauchy. Because we're assuming the fibers are complete, they have to have limits, and you can just take the corresponding limits to define a new section with, again, finite infinity norm, finite infinity norm. That doesn't sound so good, but yeah, you get the idea. Okay, so I'm afraid I might just have to take a quick break. So just you can look at this for a second, but I will be back in like 3 minutes. Just hang on a second.
Okay, so we're back. So everyone hear me again? Sorry for the interruption. Okay. So I think, yeah, I think we're still recording. All good. Okie dokie. So what was I just saying? I was just saying that when you look at sections with finite infinity norm, then this indeed forms a Banach space because it's complete. Certainly a norm space, but the key thing is completeness. Okay, what about the 2 norm? So is this, oh no, hang on, like my screen sharing doesn't seem to be working. Resume share. Ah, okay, all good. Okay, what about 2 completeness? So we claim that in fact this is also true when we look at sections with finite 2 norm. They again form a Banach space. They again are complete, but this time, of course, with respect to the 2 norm, not the infinity norm. Okay, so the proof is not so hard, but like let's do it. So let's take some 2 Cauchy sequence. So Cauchy with respect to the metric you get from the 2 norm. Okay, well, in particular, if it's 2 Cauchy, then it has to be infinity Cauchy, right? Because the infinity norm is dominated by the 2 norm. So as we just mentioned, this means there is indeed an infinity limit, which is just the limit within each respective fiber of all those values, right? Or put in other terms, what it's saying is the infinity norm of a minus an goes to 0. Okay, in particular, for any finite subset, again, I think I've got this gamma, this should be a G, sorry about that. Again, if you restrict to any finite subset now, well, then I can look at the 2 norm of that and say, well, I can replace the a here with actually am. And as long as I take the limit as m approaches infinity, this shouldn't change, right? Because I guess maybe it's a little hidden here, but because I'm restricting to a finite subset, the 2 norm is in fact bounded by basically a sum of a finite sum of norms in the corresponding fibers. At every single point, the value of this at that point in the groupoids will just be a finite sum from individual will come from basically a finite sum of star squares of am and an, right? So it's key to be able to do this that really I'm restricting to some finite subset here. Okay, but what do I know? Well, I know the 2 norm of something restricted to f has to definitely, by definition, be below the 2 norm of am minus an. And we assumed at the very beginning that we're dealing with some 2 Cauchy sequence, an, right? So 2 Cauchy means I could pick my n here to be large enough so that the terms here, and in particular the limits of these 2 norms here, have to in fact be as small as I like, right? Okay, so the 2 norm of a minus an therefore has to be, well, it's the supremum of all these guys, right? So it has to be below, in particular, the limit as m approaches infinity of this. So at this point, I guess I'm sort of fixing some n here, right? Okay, but now I can use the fact it's Cauchy to say, well, okay, if that's true, then if I let n approach infinity now, and I can make this as small as I like, therefore this limit actually has to be 0. And what this tells you, therefore, is that an is by definition the 2 limit of, a is the 2 limit of an, right? Well, originally we only knew a as the infinity limit of an, but using this little trickery here, we've been able to show that a is also, it turns out, the 2 limit of an. Okay, and in particular, well, I can just again fix some almost arbitrary n and just pick any n such that this 2 norm is finite, and then use subadditivity to show that a itself is also within this subspace S turbo, that it also actually has finite 2 norm. Like we know this has finite 2 norm. By definition, an lies within S2, so it also has to have finite 2 norm.
So we found something which is a 2 limit of an and which is also has finite 2 norm. And that's what we wanted to show. That shows you that the space we have here is indeed 2 complete. Okay. And using that, we can build that up now to the B norm. Right? Oh, whoops. Okay. Okay. So how do we do that? Well, so again, this time take some B Cauchy sequence of sections. So all these guys have finite B norm, and we're claiming that they feel like they should converge, that they're Cauchy with respect to the B norm. And again, arguing like before, right? This in particular tells you that they have to be 2 Cauchy, because the 2 norm now is dominated by the B norm. Okay, and so again, kind of like before, just using 2 rather than infinity, we know that we have some 2 limits A, right? In other words, we have some section with finite 2 norm such that the 2 norm of A minus AN goes to 0. Okay, so for any finitely supported section now, so before we were using finite subsets, but now because we're looking at the B norm, we have to consider finitely supported sections. So if we look at the product of A minus AN times this finitely supported guy, then we know that this approaches 0. So again, it's essentially the fact that F is finitely supported is quite important here, right? So we know the individual 2 norms, sure. So when you're looking at some convolution product with a finitely supported guy, then the sums defining this are all going to be finite essentially. Okay. So we know this is true, and again, what that tells you then is that I can replace A here with AM and just take the limit as M approaches infinity, at least when I'm restricting to a product with some finite element here. So if this 2 norm has to be the same as this 2 norm here, the limit as M approaches infinity. And now that we know this is, again, finitely supported, by definition of the B norm, this has to be below the B norm of AM minus AN times the 2 norm of F. Okay, but again, this is Cauchy, right? So if this, well, firstly, if this is true for all F, then by definition, the B norm of A minus AN, right, has to be below this limit here. Okay, but because we're Cauchy, I can choose my n here, which at this point is fixed, and I can basically make it as large as I like. So I can make this, because it's Cauchy, as small as I like, which means that the limit as n approaches infinity of the B norms now does indeed approach 0. So that means that A is not just a 2 limit now, but again, a B limit of the AN. And again, with this sort of little observation like we had before, you can pick some arbitrary n such that this is finite, use subadditivity to show that the B norm of A itself, the limit now, is also going to be finite. And so in the end, you found some element with finite B norm, which is a B limit of the original B Cauchy sequence AN. So completeness, again, holds. Okay, so we've done a lot of abstract proofs. I thought maybe at this point it's good to give a kind of motivating example. So let's consider the discrete group void, which just consists of all pairs of natural numbers, right? Where the product is like we were mentioning either last week or the week before, where the product is just defined as you would expect. So products are defined when the right term here is the same as the left term, and in which case the product itself is equal to the remaining terms, L and N here. And the inverse in this group void just switches the order of the pair. In particular, we can look at a trivial fell line bundle over this group void, right? So we just look at the product with C, usual product topology, and look at the canonical projection of this this double or triple product here to n times n, explicitly defined like so. So then you consider sections of this fell line bundle, and you see that what we're really dealing with is some kind of infinite complex valued matrices, right? Every section has to be of this form, where the A underline here is exactly like I said, some function from n times n to C, which is really just an infinite matrix, right? We can identify the sections with infinite matrices, and then you can see, well, what do these norms really correspond to? Well, the infinity norm of some infinite matrix in this case is just the supremum of the moduli of all the entries, or the individual entries in your matrix. The 2 norm, on the other hand, this is the supremum of the norms of all the columns of your matrix. When you view these columns as elements of the Hilbert space, little L2, right? The infinite dimensional separable Hilbert space. The B norm now is the norm of the matrix when you associate the matrix with an operator on L2, right? I mean, not every matrix does have an associated operator, but this is what the B norm is basically telling you. If the B norm is finite, then this will indeed define a bounded operator on L2. And the operator norm is precisely the B norm in this case. So that's sort of one example I think you should have in mind when you're looking at these norms. These are the kind of things you're dealing with. There's something a bit special about this example. I mean, it's very special because it's a trivial Feld line bundle. There's no twisting or anything like that. But in particular, the fibers are one-dimensional. And so what that means, various things I guess it means, but one thing that tells you, in fact, is that when you have finite 2 norm, some section has finite 2 norm, that automatically implies that the product of A star and A is actually defined. I mean, if you think about the product of A star A, because it's one-dimensional, these operators in the unit fibers, when you're looking at the sums defining this term, they can only increase in 1 dimension, right? Whereas if you had a general Feld bundle, then the unit fiber might be very large, and it could, increase in many directions, but never actually approach anything. Whereas here, because it only has 1 direction, if it's finite, then it actually has to approach that finite value. And what that means is that you can easily define a Hilbert module structure on S2, right? That this product of A star B is well defined. We'll see why this is true very soon. And that in turn allows you to show that the elements with bounded B norm form a C star algebra. And this B norm here is indeed the C star norm. For general Feld bundles, however, this is no longer true. So you have to be more careful. So in particular, you can't just automatically say that having finite 2 norm implies that A star A is defined. What you have to do is basically restrict further to the elements which have finite 2 norm and such that A star A is defined. This is the only way we can really get out of this if we want to get a nice C star algebra at the end. So this is what we look at next. So first we have to sort of examine a few basic properties of what I call star squares. So star squares are just elements of this form, A star A. So let's take a section. Let's assume, well, let's look at the star square. Now the claim is that the star square is defined precisely when these 2 norms here can go to 0, where you're taking the limit, but at some x here. You're taking some unit x, looking at all the finite subsets of that, right? All the finite subsets of the groupoid which have source x, basically. And then looking at the remainders, right? And looking at the 2 norm of that. And the claim is that this is defined precisely when this goes to 0. So it does show that, I guess, that when A star A being defined is very closely related to the 2 norm, but it's not just saying the 2 norm is finite, it's saying something else, right? Okay. So one direction is kind of simple. Notice that if A star A is defined, then by definition the 2 norm of this is simply the norm of this at x, right? Because we're fixing x here. And the norm of that at x, well, for A star A to be defined, this has to converge to this, right? So if this converges to this, then by definition, the norm of the difference has to go to 0. Okay, so that's sort of the easy part. The slightly more tricky part is to basically move from looking at units to looking at more general elements now. So if we conversely assume that this star here is true, and we take some arbitrary element G now, so it doesn't have to be a unit, and we look at some finite subsets, F and E of G, big G, little g. So this is just the elements of the groupoid whose source is the same as the source of little g. So the Cauchy-Schwarz inequality for Hilbert modules, right? Basically looking at as we did last week, you're looking at this Hilbert module defined by taking the sum of the Hilbert modules corresponding to the fibers which share a source with G, right? Then you can see that inequality tells you that the norm of the difference of these guys at G is exactly, well, it's equal to this by definition. And then Cauchy-Schwarz tells you that this is in fact below the norm of A restricted to this subset here. So the elements of E that are not in F times G inverse times the 2 norm of A, E, F, right? I mean, if you write it out in full, this is what you'll find. Okay, but we know the 2 norm of this indeed has to approach 0, right? Like just rewriting what this is. Well, this is the 2 norm of some expression of this form here, right? And well, if that's the case, then this has to, yeah, hang on, let me see what's approaching 0 here exactly. So but 2 norm of this is 2 of that. Okay. Okay, so I'm trying to think. I mean, yeah, I'm saying it approaches 0, but I guess I haven't been very precise about what I mean. What I mean is that as both E and F, I guess, get larger. So it's a Cauchy net essentially. So as both of them get larger, then these things approach 0. I guess it doesn't. Yeah. As long as E is bigger, then this is true, right? Okay. Yeah. So F and G is Cauchy. Yeah. So I'm really talking about Cauchy nets here. Until now, I think I've really been restricting to Cauchy sequences, but you can easily generalize the notion of being Cauchy to nets over some directed set. In this case, the directed subset of like all finite subsets of big G, little g, right? And so if Cauchy sequences converge, then Cauchy nets also converge. And so what I'm saying is that you had this Cauchy net. Or I guess another way to look at it would be to take some enumeration of these and then look at the corresponding sequence. But yeah. So I guess I should have maybe been a bit more precise about like what about Cauchy nets. But hopefully this is somewhat understandable. Okay, so you get this Cauchy net here, and we know it's well, Cauchy nets have to converge in this fiber here because these are supposed to be complete. Okay, and so we know it has some limit, right? And as this was arbitrary, well, this shows that in fact the limits always exist at all G, which is by definition what it means to say that A star A is actually defined. Right? Okay, so now we can finally prove something, more C-star algebraic. We can finally show that this B norm is at least acting in some way like a C-star algebra norm, that it satisfies this key C-star norm equality, right? And the way we have to do that is to prove something similar basically for the 2 norm and the infinity norm. I mean, this is basically what we already proved. Remember for the only issue is that if we were to restrict this A here to some finite subset and take the supremum, then by definition, that would be equal to the 2 norm of A squared. But the point is that we're saying if A star A is defined, then you don't need to take supremum over finite restrictions or anything. You can just look at the actual infinity norm of that product, or alternatively, that product restricted to the unit space. Doesn't matter. Okay, so this should be true, and then using that, this should give us this C star norm equality. Okay, well, so as I was, as we know A star A is defined, what that really means is this A star AF at any fixed X has to approach A star A at X. And if this approaches this, well, then of course the norm also approaches this, right? The norm itself is always a continuous function on any norm space. So what this is saying is that, okay, so for each unit X, if I look at norm of A2 squared, what do I get? Well, so by definition, the 2 norm squared is equal to this. This is the 2 norm. And what else? So So as I said, this approaches this, so I could really write the supremum as just already the actual value of A star A. This has to increase to this. This is certainly below the infinity norm of A star A without any restriction at all. And remember this inequality we proved a while back that the norm of the infinity norm of A star B has to be below the product of the corresponding two norms. So in this case, A is equal to B. So this is below the two norms squared. And this appears on both the left and the right. So in fact, this inequality here, these two inequalities have to actually be equality, right? So that's half of what we wanted to show. So that shows that this top sequence of equalities holds. To get the C star norm condition for the B norm, again, take some finitely supported section. Again, look at the two norms squared. Using this this alternative characterization, I guess, of, or is it no, or is this isn't the alternative characterization? Yeah, I think I'm basically using the same, but isn't it inequality? Hang on a sec. Yeah, I mean, okay, so this is what I've already proved. I've already proved this just using this first equality here, but now just replace A with AF. Okay, that gives you this first inequality here, first equality. And then we know from our alternative characterization of the B norm that this is indeed below the B norm of A star A times the B norm of F. And this you've got two F's here, so it's going to be the two norm of F squared. So now divide by the two norm of F squared, and this tells you that the B norm squared has to be below A star A, B norm. It's exactly what we wanted to show. Okay, and that's, oh yeah, this is only really one direction, whereas the other direction is fairly immediate, right? Because we know that the B norm is submultiplicative, and we know that the B norm is star invariant. Okay, so that immediately gives us the other inequality we need. Okay, so I mean, this is a bit of a long slog, but we'll get there eventually. So next we want to look at products and say something more about when they're actually going to be defined, not just star squares, but actual more general products. So let's take some element with finite two norms, some section with finite two norm, and let's assume that we have another section B such that B star B is defined. So knowing that the star square is defined, knowing that A has finite two norm, we claim actually implies that the product of A star and B now is also defined. So to do this, we sort of argue a bit like before. So we take some fixed element of our groupoid. We take two finite subsets, F and E, F included in E. Now recall that the Cauchy-Schwarz inequality again. So this time, which one am I using? I guess I'm using the Cauchy-Schwarz. Am I using Cauchy-Schwarz for Fell bundles, or am I using it for Hilbert modules? Okay. I guess because I'm looking at a fixed G, I think I'm using it really for this Hilbert module, again, restricted to one of the fibers too. Okay, so this first part is kind of easy, right? Restricting to E minus the restriction to F, but F is contained in E, so this is really just B restricted to the difference, E not F. What we know is that, yeah, this is the Cauchy-Schwarz part, right? That this is going to actually be less than or equal to the two norm, but at this restriction here, right? Whereas again, it's going to be the two norm of B restricted to E not F. And then finally, because the two norm is, I guess, monotone, we know that this is definitely going to be below the two norm of A itself, and the two norm of taking E to B, or letting E approach the entirety of big G, little g. All those elements in the groupoid which share a source with little g. Okay, so again, I'm using Cauchy nets, right? So this tells you that this is actually a Cauchy net now, and thus this is Cauchy, and yeah, because we know that this limit here has to go to 0. This was this defining, or this alternative characterization of when B star B is actually defined, right? That these norms, these two norms, have to go to 0. So A2, we know A is, by assumption, it has finite two norms. So this we can just replace with some fixed finite constant. And we know that the remainder here, these two norms here, they approach 0. Okay, so this tells us this is a Cauchy net, so therefore as BG is a Banach space in this particular fiber, this shows that this A star B of G, the finite sums defining that really do converge, and therefore this is actually defined at G. And as G was arbitrary, well, it's defined everywhere. So that's just saying A star B itself is a well-defined section. Okay. So that's going to help us a little bit. What it really tells us immediately, in fact, is that we can look at this subset of elements with finite 2 norm such that A star A really is defined. And then we have this well-defined inner product, if you like, on H of rho. The H, if you're interested, is because we will show very shortly that it defines a Hilbert module. Okay, but thanks to this lemma here, we know that we can actually define A star B and of course define its restriction to the unit space as well. Okay, and not only is this a subset, it really is a subspace, right? We can certainly multiply by scalars and that won't change the fact that this is defined or this has finite 2 norm. But moreover, if we look at the sum of 2 elements in this subset and we just expand out the product, right, A plus B star, A plus B, then we find that is again well-defined. And well, it certainly has finite 2 norm as well because the 2 norm is subadditive. Okay, so we have this subspace now of S2, which we're going to examine. And the claim is that this actually does give us a Hilbert module. So the first thing to note is that we get a C-star algebra. We wanted to show that, you know, these sections, more general sections are C-star algebras. But one thing we can actually note immediately is that if we restrict to sections which are supported on the unit space, then these do indeed form a C-star algebra. So in this case, convolution just reduces to pointwise multiplication within the unit fibers. And if you look at the infinity norm, this is actually the same as the B norm, same as the 2 norm when you look at these unit supported, if you like, sections. So this definitely forms a C-star algebra. And if the fibers are one-dimensional, for example, this will even be a commutative C-star algebra. And the claim is that this forms a Hilbert module over this diagonal subalgebra D of rho. So, well, does it form even a module in some sense, right? Can you actually multiply by D and then take it outside of the inner product? Well, there are just a few elementary calculations so that yes, right? The fact that D is supported in the unit space means that when you multiply by B before taking the restriction, it's the same as multiplying by D after taking the restriction to the units, right? So it's definitely a module, a DP module. The main question really is whether it's complete with respect to the norm that you actually get from the inner product. But note that the norm you get from the inner product here, right? This is really just the same as the 2 norm. And we've already shown completeness of those elements with finite 2 norm. We just have to show that when we restrict further, that again, the resulting limit lies within H of rho. So let's do that. Let's take some 2 Cauchy sequence AN within H of rho. Okay. As I just mentioned, we do know there is some limit in S2 of rho. The only question is whether this element A here also lies in HP, whether A star A is also defined. Right? And to see that, we use this lemma we had before, where we restrict to all elements of we take our A and restrict to GX not F, for finite F. Right? Look at the 2 norm of that, apply subadditivity of the 2 norm, and we see that what we end up with is the following, right? And well, we know that A minus AN 2 norm, that this approaches 0 as it approaches infinity. We also know that each AN individually is the star square of that is defined, or in other words, that as F gets larger and larger here, these 2 norms approach 0. That was our alternative characterization of AN star N being defined, right? So these approach. So if you, in the end, what you end up with is knowing that the limit of this has to be below A minus AN 2 normed, but we know that as N approaches infinity now has to go to 0, right? Because, well, it's a 2 limit. Right? And that is what tells us that indeed, from our other characterization, that A star A itself is also defined, and hence A is within rho, H of rho. So let's now look at these elements with finite B norm, and let's in fact look at them as if they're kind of operators on H of rho. I mean, it's not immediately clear that we can really do this, but it turns out yes, that as long as B is within H of rho, then AB is defined. I mean, that I guess, let's see. Yeah, I mean, we want to show that's actually defined. We already have this, and in fact, more specifically, we want to show the resulting product is the 2 norm of the resulting product has finite 2 norm, right? And specifically, you can bound it in the way you would expect, that the 2 norm of AB is below the B norm of A times the 2 norm of B. So it shows the B norm is not just the operator norm when you're looking at it as an operator on finitely supported sections, but even these more general sections which have finite 2 norm. Okay, so we already know that AB is defined, right? Because, well, the 2 norm of A star is below the B norm of A star, which is the same as the B norm of A, right? Which by assumption is infinite. And we had this result, right? That if the 2 norm of the star of the guy on the left and the 2 norm of the guy on the right are both finite. And okay, so yeah, this was, let me see. Yeah, it's this result here, right? That if the 2 norm of this guy is finite, that B star B is defined, then A star B is defined. So all we're doing is using that result here, together with the observation that the 2 norm of A star is bounded by this finite B norm of A itself. Okay, so that's one issue. Now, what do we want to show? We want to show that the AB is actually has finite 2 norm. So, well, let's look at the 2 norm of AB with some finite restriction here. So again, we're looking at finite sets, F and E, right? F contained in E. So the 2 norm of that, well, then we use the definition of the 2 norm to say this is bounded by the B norm of A times the 2 norm of that, which is definitely bounded by the 2 norm of this larger restriction over here. And what this tells you really is that, well, again, this we can replace with some fixed constant because we know that A has finite B norm. We know that B star B is defined because B is within H rho. This was the definition of H rho. So we know that this approaches 0 as the F's get larger and larger, right? And so in the end, what this tells you is that this is a Cauchy net, a 2 Cauchy net, right? Okay, and so in particular, this A star B here, right? Sorry, this AB. So this AB is by definition, the pointwise limit, right, of AB, F. It's all these finite restrictions. Okay, so if it has a pointwise limit, well then, and it's 2 Cauchy and it has a 2 limit, well, the 2 limit and the pointwise limit have to coincide, right? So if we look at the 2 norm of that, well, that's going to be the limit of the 2 norms of the finite restriction because this approaches that. Okay, but then again, applying some inequalities, in the end, you say this is bound by the B norm of A and the 2 norm of B. And this is true for some arbitrary fixed unit X, right? So if this is true, this is showing you that AB itself has a 2 norm bounded by this product, the B norm of A and the 2 norm of B. Now we can go back to associativity, but this time we're going to do it in a more general setting. So remember before, at first, we could only prove associativity when either the leftmost or the rightmost section happen to have finite support. Now we can do it in a bit more general. So let's say we have something with finite B norm. And this is the corollary I have to prove before I get to this. Okay, so the previous result was saying that okay, AB has finite 2 norm. So if you like, it's really saying A is an operator, but not exactly an operator on H of rho. It's really an operator from H of rho to this larger Banach space S2 of rho. And the natural question you would ask is, well, when is A itself actually an operator on H of rho? Like is this true for arbitrary A, or do I need some further restriction on A to ensure that the the result of the product is again within H of rho. And we do need a bit of a restriction. So instead of just assuming that A has finite B norm, we need to assume that A also lies within H of rho. Then we can show that the resulting product again lies in H of rho. So to prove this, okay, we again want to use this. Well, we want to use the fact that we know H of rho is complete, right? So let's see. Well, take some fixed unit, take some finite subset consisting of groupoid elements whose source is X. Look at the corresponding product when B is restricted to F. Well, we know that's within H of rho, basically because this is a sum. You can imagine this B restricted to singleton elements that make up F. So if you multiply A by some singleton supported element, and A is already in H of rho, then it definitely, again, has to be within H of rho. I guess what that really boils down to is the submultiplicativity of the norm in all of the fibers. So if that's true, and this is just a sum, we know that H of rho is closed under finite sums. So therefore, AB restricted to this finite subset is again going to lie within H of rho. Okay, but then you know that this AB restricted to big G of X now. Okay, that has to in fact lie within H of rho because this approaches this, right? And if this approaches this in the 2 norm, and we know that H of rho itself is complete, we just proved that. Well, therefore, this also has to lie within the completion, which is itself, right? Okay, so that's just the sort of quick corollary. And now the corollary which I was getting to before, and that is this generalized form of associativity. Now, instead of assuming that either A or C is finitely supported, we just have to assume that A star or C lies within this larger space, H of rho, this larger Hilbert module. But again, the middle guy has to be, I guess it is more restrictive in the sense the middle guy has to actually have finite B. But these are the ones we really care about. So we want to show that it doesn't matter which way we take the product. Why is that true? Well, firstly, we know that these are defined, right? We know that, again, it's following from the results we already had. So we know that BC is going to be an element of S2. That's true, right? Because, okay, look, B is within SB and C is within S2. And I think we showed before that the previous slide that AB itself then has finite 2 norm. Okay, so that's true, that's true. And then again, going back a few more slides, when you have a product of 2 things with finite 2 norm, or at least the star has finite 2 norm, then the product is again well defined. Okay, so they are well defined. That's good to know. Now let's look at what their values are at when we restrict to, say, groupoid elements with source X. Okay, and let's in fact compare them with the restrictions to some finite subset of GX. Well, again, this is sort of the easy part. And now we're looking at, well, we know that AB, using this inequality we had before, we look at a product of elements in the infinity norm. Well, that's bounded by the product of the corresponding 2 norms. But then using the definition of the B norm, you get this in the end. Well, the definition of the B norm, not exactly the definition, I guess, because again, A star may not be finitely supported, but we showed before that we can actually extend this inequality to A stars, which are lying within your Hilbert space. Okay. The same applies here. We're just doing the product in the other direction. But now we can use the facts. Well, now we can, what can we do? Well, now we can use the fact that this and this are the same, right? We did know that when C is finitely supported, in particular when we restrict an arbitrary C to some finite subset, that it doesn't matter which way we take the product. And so therefore subadditivity in the infinity norm says that these 2 different ways have to be bounded by the sum of these 2, which is so just 2 times these guys right here. Okay, but we know, what do we know? Well, so this has to approach 0. Why? Well, because A star has finite 2 norm, B has finite B norm, and this, because C star C is defined, this has to approach 0 as F gets larger and larger. Okay, so these do indeed, this infinity norm is bounded by, in the end, 0. So in fact, these 2 things are exactly the same. And because we restricted to g of x for some arbitrary x here, well, in fact, it shows the whole things are the same. I mean, basically, this equality is telling you that the two products here, ABC and ABC, they are the same on all groupoid elements with source x. Okay, but if x was arbitrary, well, then they're the same everywhere. Finally, we're going to get to a C star algebra. I'll call this the big C star algebra for want of a better term. So let's call it B of rho. So we get a C star algebra. I'll call B of rho, with the norm being, of course, the B norm, which consists of all those elements with finite B norm, such that both A star A and AA star are defined. Or if you like, it's the intersection of the Banach space SB of rho, together with these Hilbert modules H of rho and all the stars of H of rho. Okay. Well, first thing to note is that this B of rho really is closed under products. I mean, basically, what do we know that the product itself lies within H rho and H rho star from exactly this result I had here. This is the result on the previous slide, this corollary right here. So we know that the product lies within H rho and H rho star, but we also know that AB itself has finite B norm, just from the submultiplicativity of the B norm, which we proved, right at the beginning. Okay, so AB is within these three, but this is the intersection of these three, so therefore it has to lie within big B of rho. We also know the product is associative for all of these elements. This is what we just proved in a more general setting, for more general A, B's, and C's. But in particular, if they all lie within the intersection of all these subspaces, well, then definitely the triple products are the same. We know that A star lies within B rho whenever A does, right? I mean, the fact we're taking the intersection of H rho with H rho star, immediately means if it's in one, then it's in the other, and vice versa, right? And we know the B norm is star invariant. So if A has finite B norm, then the exact same bound applies to A star. And again, we know the B norm is subadditive. We know the B norm satisfies the C star condition, right? These key defining properties. I guess the last thing we really have to check yet again is that it's actually complete with respect to the B norm. So far we only know it's I guess a pre-C star algebra in some sense. So for completeness, take some B Cauchy sequence AN. Then we so we know that it has a limit, a B limit, right? This was what we did before, showing that this is a complete Banach space, right? The only issue is, do we also know this lies in HP and HP star? Well, yes, we do, because we know the 2 norm is bounded by the B. Okay, so, and HP, again, we already showed this is 2 complete, therefore, this limit, I mean, it has to have a 2 limits, and 2 limits, they're going to be unique, so the 2 limit has to indeed be the same as the B limit, it has to be this A. And again, like exactly the same happens with A star. So we knew that this limit here really does lie within big B of rho. Right. I mean, I guess there's maybe other things you would like to check, like that the product distributes over addition. So A of B plus C is equal to AB times AC. But all of the other things are fairly immediate, fairly straightforward. We've already dealt with them essentially when dealing with Banach bundles and sections of Banach bundles and taking sums there. Right? These are really the extra things we had to check. And using all these equalities that we managed to develop over the course of the lecture, we can show that we get a C star algebra. But it's not quite the C star algebra we want. It's not the reduced C star algebra that really is our ultimate goal to define. So to define that, we have to go back and use the topology. I mean, up until now, we haven't really used the topology of B at all. We've been dealing with completely arbitrary sections. So now we really want to look at continuous sections again. And in particular, we want to start with these compactly supported sections. Okay. So recall that, this is just the notation that CC of P refers to sections which are continuous and such that they have, this is not quite right. The closure of the support, I think, should be compact, not the support itself, right? The support itself will generally be some open subset. So you want to take the closure and say, well, that has to be compact. We'll actually also be interested in even more restrictive kinds of sections. We'll be interested in those which are supported on some slice, some bisection of the groupoid. And the theorem is that we will need is that as long as you have a locally compact Hausdorff tile groupoid, as long as that's the base of your Fell bundle, then indeed every compactly supported continuous section is actually just a finite sum of slice supported, and still compactly supported continuous sections of rho. And it's a fairly kind of standard, partition of unity kind of argument. So the first thing you note is that we can cover the support of A, or even its closure, with some finite collection of relatively compact open sets, right? Open, and not just open sets, I should say, open slices. I should have specified this, right? We're trying to get, it's a finite sum of finite slice supported elements. Because we're dealing with an Natal groupoid, every point has a neighborhood, which is a slice. And so you can, at every point, you can take these slice neighborhoods by compactness, then you can restrict to some finite subset, which is still going to be a cover of the closure of the support. Okay. So, hang on a second, I just want to. Okay. So we cover it with all these open slices because we're locally compact Hausdorff. We have this partition of unity. So hopefully you're familiar with this term. So it's you're covering the whole space now with these O's, but also you've got like one thing left over at the end, I guess. I guess this should really be the closure of, well, yeah, the closure of these guys. Yeah, I mean, don't worry too much about this last set here. The point is that you can have these scalar valued functions where the scalars take values between 0 and 1, and you can ensure that they partition at least the support of your original section A, in the sense that well, all these, they're subordinate to the OKs, so all the supports lie in OK, and when you take the sums, you end up with 1, at least on the elements in the support of A. You would have to have some additional function if you wanted it to be 1 elsewhere, but we don't care about that. So in particular, we can look at the product of ZK and A point-wise, right? This is not a convolution product in any sense. We're just saying at each individual G, we look at the value of ZK of G and multiply that by the original value of A of G. So the ZK is a continuous, the A is a continuous, so it's again continuous. Okay, but moreover, because ZK is supported on some open slice, then AK is also supported on some open slice. And because they all sum to 1 on the support of A, then the sum of all these functions gets you back the original function A, the original section A. Okay. The reduced C-star algebra. Now we are finally in a position to actually define this. So notice that if you have something which is slice supported, then these sums which define A star A, these finite partial sums, are not just finite, they're really sort of singleton sums. They're only going to have at most 1 non-zero term, right? I mean, essentially because you're looking at sums of the form AG star AG, right? But for all G's which have a common source. And there's only, if the support is a slice, then there can be only at most 1 G with a fixed source, which is non-zero. Right? That's what being a slice is, right? The source and range maps have to be injective on any slice. And then it's sort of just a short step away to realize that, well, definitely A star A is defined in that case. But moreover, the norms now all collapse to the same thing. That the infinity norm is the same as the 2 norm. That's a fairly immediate calculation. Pardon me. I guess with the B norm, maybe you have to be a little bit trickier to actually find out exactly what this is. But in the end, you can, not too hard to see, the B norm of A is again the same as the 2 norm of A, as long as the support is a slice. And moreover, that these will indeed be finite as long as A is compactly supported, right? The image of a continuous function, in this case, I guess the map taking the element of the groupoid, the norm of the value of A at that point, That gives you a continuous function, or sorry, actually an upper semi-continuous function. But nonetheless, this will be bounded because the support is compact. Okay, so what does this tell you? Well, this tells you that in fact these compactly supported sections all lie within this big C star algebra B of rho, right? Like if you express this, you can express this as a finite sum of guys, which we just mentioned, all lie in B of rho, but this is a C star algebra. This is in particular closed under sums, finite sums. So therefore, these all lie within B of rho. And that gives us a very easy way, finally, to define the reduced groupoid C star algebra. We just define it to be the C star subalgebra of this bigger C star algebra we've already been working with, this B of rho. So it's just the closure with respect to the B norm, right? That is important. We have to use the closure with respect to the norm topology defining the C star algebra structure of B of rho. Okay, and well, one thing to point out is that sure, we're using the B norm to define the closure, but anything that is in the B closure, if you like, will definitely also be within the infinity closure because the infinity norm is bounded by the B norm. And the infinity closure of this is really just the sections which vanish at infinity. Okay, so so what this tells you is that these more general elements in the reduced C star algebra, even the ones that were not compactly supported, the ones which are limits of compactly supported guys, that the resulting limit is again going to be a continuous section which vanishes at infinity. Right? I mean, the fact that it's continuous, I guess, is basically amounting to the fact that whenever you have a uniform limit of continuous functions, that the resulting limit is again going to be continuous. So you can, in particular, do this with these trivial Feld line bundles that I mentioned before. So you just take any locally compact Hausdorff tile groupoid G, look at the product with complex numbers, look at the canonical projection. That gives you a trivial kind of bundle. Okay, in this case, the reduced Feld bundle C star algebra is really the reduced groupoid C star algebra that we looked at some lectures ago, which we originally defined as the completion of the compactly supported elements with respect to this regular representation, with respect to the operator norm you get from the left regular representation. The downside of doing things in that way was that we didn't really know what these more general elements in the completion really were. I mean, they're operators, definitely. They were operators on this Hilbert space, but we didn't have any idea of whether they also corresponded to any kinds of continuous functions. But the way we've been doing things in this lecture, even though it took us, I guess, a bit longer to actually finally get the result we wanted, the end result was that we do still realize even these more general elements in the completion as concrete, continuous, complex valued functions vanishing under infinity, where the product is again still the convolution product. Before you didn't really know anything like that, right? You had this sort of abstract completion, or if you like, a closure in a space of operators. So the product is definitely the operator product in the usual way, but we didn't know that it corresponded to sections. We didn't know that the product is really convolution. But now that we've done things in a more sort of, what's the word, a more concrete way, which took more effort, but in the end gave us what I think is a better result. Certainly for me, I feel a lot happier knowing that the elements in my reduced C star algebra here really are concrete functions now. There's always in a lot of, even in the literature these days, a lot of sort of dancing around the fact that elements in the completion aren't immediately, at least, obviously represented as actual continuous functions. But yeah, this shows that there really doesn't need to be such a big debate. One final thing to point out, which is again quite important, is that even though, like I said, these elements in the reduced C star algebra are or can be identified with actual functions, sections, sections of the trivial bundle, vanishing in infinity, that this inclusion can be strict. In fact, it very often is strict. So if we go back to this example that I mentioned some time ago, where you were looking at just this groupoid consisting of all pairs of natural numbers, so that your sections in this case are basically just infinite complex valued matrices, then if you can consider one section where you basically set the matrix to be 1 over root n along the diagonal and 0 everywhere else, then you will indeed get an element of the reduced groupoid C-star algebra. Right? You can indeed approach it by compactly supported elements. However, if you instead set not the diagonal, but if you set this be one row, so the top row to be 1 over root n and 0 everywhere else on all the other rows, then you'll see this is not actually an element of the reduced groupoid C-star algebra. I mean, essentially because this matrix, it doesn't define a bounded operator on finitely supported guys, and therefore it doesn't define any operator on the entire Hilbert space little L2, right? Or put another way, you can't approach this with respect to the B norm via compactly supported functions, i.e. matrices with finitely many non-zero entries. Sure, you can approach it in the infinity norm, right? But you can't approach it in the B norm in that way. That's the problem. And this is sort of coming to the end of this lecture and hence the whole course. I mean, maybe just before I leave, I want to point out some further directions in which you can go. We don't have time to cover anything like this in this course, unfortunately, but it might be instructive to know what kind of things you would like to know if you want to keep going in this direction. So, I mean, one of the things you can do, of course, is now that you've got this nice construction from a groupoid or a Fell bundle, you know, of a reduced C-star algebra, then you would want to, you know, show how various properties of the Étale groupoid actually give you, you know, certain properties of the C-star algebra. Okay, so for example, one thing that C-star algebraists are very worried about a lot of the time is whether their C-star algebra is simple, right? And this turns out to be intimately related to the groupoid, in particular, whether the groupoid is what's known as minimal and effective. Okay, these give you criteria which allow you to show your C-star algebra is reduced C-star algebra is going to be simple. Okay, and there's many other conditions as well, which, I mean, the whole point of looking at groupoid C-star algebras really is to give you a better handle on the C-star algebra using the groupoid. So of course there should be lots of results of this form saying if G satisfies blah, then my C-star algebra satisfies blah. And that is indeed what we find. Another thing that is definitely, you know, I think quite a hot topic of research these days is to do with Cartan subalgebras. So this diagonal didn't really play a huge role in our work here, but this diagonal subalgebra turns out it satisfies a few very natural properties. There's a natural expectation just by restricting to the unit space essentially, and the normalizers generate the whole thing at least when G is effective. And so this tells you have a Cartan subalgebra of not C of G, this should be CR of G, right? And that's already something worth pointing out. But the really interesting stuff is that, in fact, all Cartan subalgebras are of this form, at least once you move from just groupoid C-star algebras to Fell line bundle C-star algebras, where there can be some kind of twisting involved. Right? So this goes back to some work of Kumjan from '86 and Renault from 2008, and various generalizations people have been looking at these days, where you show that the Cartan subalgebras have to in fact arise from Fell line bundles over effective groupoids. And the way you do it is you somehow use the Cartan to actually construct a bundle. So you're sort of going in the reverse direction to what we did today. Today we are saying, well, from a Fell bundle, I can create the reduced C-star algebra. This is saying from a reduced C-star algebra, together with a special kind of subalgebra, I can actually create a bundle on which the C-star algebra does become the reduced C-star algebra of that bundle. So this is very interesting stuff. I should point out, as I think I did when I introduced the reduced groupoid C-star algebra, that there is this other well-known maximal completion of CC of G, or CC of rho in this case. So you can indeed define the maximal Fell bundle C-star algebra in almost exactly the same way as the maximal groupoid C-star algebra. You're just dealing with sections rather than functions. Then, I mean, this is certainly something worth considering, but the key point, I guess, is that there is no way in general of showing that the elements in the maximal C-star algebra really do come from concrete continuous sections. Right? All the work we did today really does not apply to the maximal C-star algebra, unless of course it happens to be the same as the reduced. That happens whenever row is amenable in a suitable sense. But in general, this does not apply. So this is why I prefer the reduced groupoid C-star algebra or the reduced Fell bundle C-star algebra, where you really do get the algebra in the end as concrete, continuous sections. If you're familiar with cross products, then you might be wondering about whether reduced to maximal cross products of C-star algebras again are somehow related to this. Indeed, they are. Using the action that defines your cross product, using the dynamical system, you can then define a Fell bundle. And as you would expect, the reduced C-star algebra of the Fell bundle is exactly the reduced cross product of the C-star algebra, and likewise with the maximum. And using the Fell bundle, I think it also provides a nice sort of tool or sort of intermediary that allows you to analyze the cross product C-star algebras using the Fell bundle. And so yeah, this, as I said, this results in many of the classic C-star algebras people look at, and some very interesting not so classical ones as well. And you can use this Fell bundle to really get a much better handle on the structure of these C-star algebras. So I think that's, yeah, so I have gone about 15 minutes over time, but yeah, I didn't think it was worth having another lecture of this. So yeah, this concludes the course. Thank you very much for attending. And well, are there any questions about what I said today, or indeed anything over the course that you would like to know? Or? Doesn't look like. No questions, comments, criticisms? No? Okay, well, thank you very much for attending again. And like I said, I will send you an email later in the week about our mini workshop and about the potential talk topics that you could work on. And so yeah, we'll be in touch, but this is it for the moment. Oh, there's something in the chat. Let's see. More chat. Okay, thank you for the lecture. Oh, okay. My pleasure. Thank you for attending. So yeah. As I said, we'll see you, yeah, hopefully see you all at this mini workshop in Prague soon. Okay, ciao.